Okay, so today we're going to be talking about reversible reactions. Now, remember how in all the reactions we've been talking about before, in which we have some reactants, and they go forward and form the products. Now, can products actually collide and reform the activated complex and eventually become the reactants? And the answer is yes, we can, or they can, and it's called a reversible reaction. It's a chemical reaction that can occur in both the forward and the reverse directions. So let me get my pen out here. Now, in this example problem right here, or example reaction, we have nitrogen and hydrogen making ammonia gas. Now, when it goes this way, that is the forward direction. However, the products, this ammonia gas, can actually split apart and form hydrogen and nitrogen. And if it goes this way, we have the reverse direction. Now, most times when we've been writing a reaction, we've been having some reactants, and then we write a single arrow to the right to form products. We've only been showing forward reactions. However, when a reaction is actually reversible, it can actually go back this way. Then we can actually write this double arrow. So when we have this double arrow, it means a reaction is reversible. It can go in both the forward and the reverse direction. So here are reversible reactions. Now, when I show you this potential energy diagram of the reversible reaction, remember, usually we have the reactants over here, and we have some energy curve, or I mean some activation energy in which we have a hill that we have to get over in order for the reaction to proceed, and then we come all the way down here and get the energy of our products. However, if a reaction is reversible, it can actually go in the other way. So we can be down here and have our products, and it can go in the reverse reaction, or reverse direction, and form the reactants. So the big thing to really... Okay, so now remember, if we're going this, usually if we just have the forward reaction, so we have this activation energy that is from our potential energy of our reactants to the potential energy of our activated complex. And then we form products. Now, if our reactants have more energy than our products, that must mean that we have an exothermic reaction. However, if this reaction is reversible and it can go from the products all the way to our reactants, now we have this big hill in which our potential energy of our reactants is more than the potential energy of our products. So the forward direction, if it is exothermic, then the reverse direction would be endothermic. And that will always be the case. If one is exothermic, the other will be endothermic. And now, in the forward direction, our activation energy is only from here to here. The potential energy from our reactants to our activation energy, or to our potential energy of our activated complex. However, our activation of the reverse direction would actually be from the potential energy of our products to the potential energy of our activation energy. So 40 minus 5. So this is really how we can show you reversible reactions. Now, I could ask you a question such as, what is the activation energy of the forward reaction? Now then you'd say from here to here. Or if I asked you the activation energy from the reverse direction, you'd have to remember that the reverse direction goes from the products to our reactants. So we would have from here to our here. So yeah. Now, our heater reaction, remember, the heater reaction is always the products minus the reactants. So our potential energy of our products and the potential energy of our reactants does not change whether we're going in the forward direction or in the reverse direction. Our potential energy of our reactants is still 30. Our potential energy of our products is still 5. So this will be 25 for both the forward and the reverse direction. The heat of the reaction is going to remain the same. And if we add a catalyst, it would lower the activation energy. So instead of going from all the way from here to here, we would go from here to here. And if we were going in the reverse direction, it would be from here to here. Now, remember when we talked about the rates of the reaction or the kinetics, and we did the lab in which we tested different factors that can affect the rate of a reaction. Now, all reactions have some type of rate. They either go fast, they go slow, somewhere in between, but they always have some type of rate that they go at. Now, when we have a closed system when we have a closed system, that is going to be some system in which we have a box or a beaker or some type of container in which the reactants and the products can't escape. If we had gas, it'd have to be completely closed. If it was just happening in a liquid, we just have to make sure that the liquid would have to stay in the beaker. And that's what it is when it's closed. Nothing, the reactants or the products cannot escape. They're in the closed system. So if we have, let's say, some water in this closed container, so nothing can escape. When these water molecules evaporate and then form gas molecules, they're going to eventually get more and more and more gas particles. So the rate of the reaction is kind of increasing, is pretty fast right away. There's a lot of gas particles that are going up. But as more gas particles eventually go into the gaseous phase, eventually the pressure is going to go up, vapor pressure is going to go up, and there's going to be less particles that are going to be able to escape because there's going to be more pressure pushing down on these liquid molecules. Now, these liquid or these gas particles can actually go back and condense into the liquid. So right away, if we had water molecules that were in a liquid, they could go into the gaseous phase. However, and right away, this reaction is the only reaction that's happening, the forward reaction. However, eventually these gas particles can go, once there's enough of them, some will actually condense back into the liquid phase. So the reverse reaction. So we kind of get this rate at which this one's going forward a lot right away. This one's going tiny right away. It has a very slow rate because there's basically no gas particles at the very beginning. And eventually, when we get more and more gas particles, this is going to go down, and this is going to go up. And eventually, we're going to reach equilibrium. And that is when the rate of the forward and the reverse reactions are equal. Now, the amount of reactants and products, and at this point, the amount of the reactants and the products become constant. And they usually are not equal to each other. But they do become constant, and I'll show you that in this next graph on the next slide. Now, it is important to remember that this happens in a closed system, so neither the reactants nor the products can leave the system. So here is a reaction in which we have nitrogen and hydrogen forming ammonia, and this is plotting the reactant and product concentration on the y-axis versus time. So if we have a container and we put nitrogen and hydrogen in it, this reaction is going to go forward right away. And we don't have any ammonium, so the reverse reaction can't go this way. We don't have any product to make hydrogen and nitrogen. We only have our reactants. So the forward reaction, is going to be going quite fast. And as you can see, here's the concentration of our H2, and right away it decreases pretty steadily, which means that this rate of this reaction, as we go this way, we're going to get less N2 and less H2, and we're going to be getting less H2 and less N2, and we're going to be forming more ammonium, and we're going to be increasing our concentration, and eventually this reaction will start going, the reverse reaction will start going, and eventually these rates will eventually become equal. Now at that point, our concentration of our reactants and products become equal, or constant, not equal. They're usually not equal. As you can see, we have more H2 and more ammonia than we have N2. So they're usually not equal, but they do usually remain constant once equilibrium is established. So at this line here, this is when we've reached equilibrium. The rate of the forward reaction is equal to the rate of the reverse reaction. Hello? Okay.